you want to understand how bare metal programming works, it's important that you understand how we write to and read from registers. In this video, I'll walk you through some examples, and at the end of the video, I'll hook up my STM32 board to my computer, and we're gonna be debugging some live code where we'll write to and read from a register. Let's dive in. Alright, suppose I have a register. This register is a 32-bit register. It ranges from 0 all the way to 31, so there are 32 bits. And oftentimes, this is how you see registers laid out in a reference manual for a given microcontroller. I have lower half, lower 16 bits, and upper 16 bit. So suppose we have this large number. It's 4,294,967,295. It's a large number, so suppose we're going to grab this number, and we're going to put it into register A. And this, by the way, here is not necessarily equal sign. It's an assignment operator that we use in programming. So what do you think will happen when we grab this large number and put it in register A? Any thoughts? Okay, assuming you did some thinking, I have some ideas. So let's take a look. Let's take a look what this number is. So it's 4,294,967,295. Oh, that's interesting. So look at the binary number. So our binary number is basically all ones. Our hexadecimal number is all Fs. Okay, so what does this mean? So this means when you put this large decimal number into register A, it's gonna put all ones into every single bit. So it'll be populated all ones all the way to bit 31. So it'll be all ones. So as you can see, we can put a decimal number into a register and it will accept it. It will grab it. However, when we look at this decimal number, we don't really see those bits. We don't see those bit placements. Well, that's one reason we don't use decimal a lot when we're programming registers. You could say, well, I could use a binary. Yes, you're right. We could use a binary. Binary could help us to understand how the bits are laid out and so forth. It is true. It would help us understand a little better, perhaps, than decimal. However, binary is harder for us humans to read. If you look at a bunch of zeros and ones, it's really hard to pick them apart from each other, especially when you have 32-bit numbers. So what do? We use hexadecimal. When we're programming registers, most of the time we use hexadecimal. So if we wanted to turn all the bits to 1, we would use this hexadecimal number. By the way, if you do not understand how binary or hexadecimal works, or you feel a little rusty, I have a video right here. So take a look. That hopefully should be helpful. Alright, let's move on. What I've got here is a mode register. I actually pulled this from STM32 L4 reference manual. It's the actual register we'll be programming today. And this register is responsible for setting modes for each pin. As you can see, this is also a 32-bit register, ranges from 0 to 31. However, we have modes. So we go from mode 0 to mode 15. In this microcontroller, we have a range of 16 pins. However, not all pins are used, so we're gonna only be using 13 pins. So we'll go from mode 0 all the way to mode 12. For each pin, we have 2 bits allocated. So let's take a look at what modes are there. So we have input mode. We have general purpose output mode. That is the one actually we'll be using. We have alternate function mode. Alright, and we have analog mode, which happens to be a reset state. We'll talk about reset state pretty soon. Alright, so we're setting these pins into output mode because I have a board and I have LEDs hooked up, and we want to turn those LEDs on. Which means we need to turn all these modes into 0, 1 for each pin. 0, 1, 0, 1, 0, 1, and we just keep going like this. Everything will be 0, 1 all the way to pin 12. Okay, and we don't care about these bits here because we're not using them. Okay, great. So let's just divide this into 4 bits. That's what I like to do. It helps us to understand what the hexadecimal number is for each 4 bits. For example, here, what is this number? 0101. So in binary, this is 5. So we'll use hexadecimal 5. So all these will be actually 5. This one will be 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 5. This one though will not be 5 because we're not doing anything with mode 13. This one will be 1. So our hexadecimal at the end of the day should be 1, 5, 5, and then 4 5s for the lower bits. Great. So this is our hexadecimal value. Do you see a problem here? Earlier, I talked about this reset state. If you don't know what reset state is when my controller boots up. You turn on the microcontroller, it comes with that state. And we're turning on port A, GPIO A. And for that, reset state is this number, ABFF, FF. And if you know what FF is, F basically is 1. So all these bits that we're about to program into our output mode will actually be 1s. And that will be analog mode. We don't want that. Sure, we can write 1, 0, 1, 0, 1, but we first need to clear these bits. We want 0, 0. We need clean sheet of paper. So in the code that you'll pretty soon see, we're gonna zero those out. They'll be all clean, blank paper, and then we're gonna write the value we want, which is this hexadecimal value here. Okay, let's dive into code. Alright, I'm in STM32 Cube IDE, and here's my code. And if you don't understand this code, do not worry about it. I'm gonna be making a very detailed video on this very code. So the area that I want you to focus is actually this mode R register, this register here. And we're gonna be reading from that register and writing to the register. So that's all I want you to worry about. I'm gonna be covering the code in the future, very soon actually. So over here I have a variable, and this just a temporary variable that's gonna store value of mode R register, GPIO A mode R register, which is right here. And we're gonna be constantly writing to that register and reading from register to see what values it has. So the first value we're expecting it to have is this one here that comes from the reference manual. All right, let's debug and see how the register value changes. All right, so we're gonna skip this one. We're not interested. Now, if you look at the mode R value here on the right, you'll see it has 0, which it should because that's how we initialized it. However, this line should change it because we're gonna read that mode R register, and it should put that value, default value, into our temporary variable. So let me click on it. Okay, and indeed our variable changed. Our variable has this value A, B, and all F's, which is normal. Now, if you remember, we need to clear those F's to start from a clean sheet of paper so that we can program it the way we want. And this next line of code does just that. Now, supposedly, this hexadecimal value we just put into GPIO A register. By the way, if you're wondering what this and equal is, or down here I have this pipe and then equal, these are binary bitwise operators in C. And if you feel rusty or you don't understand it, I have a video over here in the corner, so please check that out. So let's continue. We hopefully by now zeroed out those bits that we're writing. Let's read it. Now we're gonna read GPIO A mode register into our variable, and we should see value change. And indeed, we have zeroed out all those bits. Next, we're going to put the value that we want, this 0, 1, and all 5s, into mode R register, and that should be the final value we want to leave it at. And that will help us to turn these pins into output mode. And let's read the value again from the register to see if that value really set. And indeed, if you look over here, our variable changed and has all these zeros and ones, zeros and ones. So we effectively were able to write that value into the register. So now pins in GPIO A, they are all in output mode. So further down the line, I'm going to talk more about how we do bare metal programming, but this lesson was just on how we write to and read from a given register. As you can see, it's very simple. Hey, if you enjoyed this video, please give it a thumbs up and check out my other bare metal programming tutorials.